Hello, my name is Ali.
My name is Jonathan.
And my name is Roxana.
Alright, and today we're going to be doing a project based on, our project question is going to be, which method is better for approximating the rate that the volume changes as we pour water into the cup? The two equations that we'll be using is the rate, the volume for a cylinder and the volume for a cone.
So our hypothesis is that the volume of a cylinder will be more accurate to determine the rate at which the volume changes as the water is poured into the cup.
Find out the rate at which the volume changes. First, we would have to figure out the rate at which the height changes pouring water using 1 second intervals.
First and the volume of a cylinder, we just have to get those equations. Once we get those equations, we would have to set it so there's only one variable in it that we solve for. Therefore, we make a ratio for radius over height for both of them, and then you solve for radius, so you can substitute that into the actual equation. So then you just substitute it into the actual equation with these values, and once you do that, you just take the derivative of it for both of them. Once you take the derivative, you plug in all of the values, which would be h and the rate of change for the height over time. And the way we got that is that we basically took different intervals, took different heights in centimeters over different time intervals, and we averaged all of that out. We got 1.09 centimeters per second. Once we got that, you literally just plug it back into the equation to get the rate of change for the volume for both of them. Once you have that, you can actually figure out the actual volume for the cup. In real life, this cup is actually called a conical frustum, and that is why there's actually equations for that. This equation is for the volume of it is 1/3 times the height times the top radius, which is squared, times the top radius times the bottom radius plus the bottom radius squared. All that equals the volume. Then after that, you would just take the derivative of this entire equation. Once you got that, you just plug in all the values, which would be h and dh dt. Once you get that, you get the actual rate of change of the volume for the conical frustum, which is 123.28. Then you just compare these two to each other. This is the cylinder, which would be 144.46. The cone would be 69.343. We can just use common sense here and figure out that 69.343, which is the cone one, will be an underestimate, and the cylinder one would be an underestimate. Then you just use even more common sense and figure out that because if it's a cone, it would be more of an underestimate than a cylinder would be of an overestimate. Therefore, you can just think that the cylinder would be closer, but the actual way you can figure that is using the percent yield, which would be the actual minus the theoretical over the actual times 100, which would be percent error. So the way to figure that out, you just do that for both the cylinder and the cone. The actual the percent error for the cylinder will be 17%, and the percent error for the cone will be 44%. And since the cylinder is less, therefore it is closer to the actual approximation for the rate of change of the volume for the conical frustum. Therefore, it is closer. So in conclusion, our hypothesis was right. The cylinder is closer to the actual conical frustum than the cone is, because the percent error is smaller than the cone. The cone is almost 3 times larger than the percent error of the cylinder.